Right, kinetic model of a gas. Kinetic theory. Can you write that down? Yep. Got that? What do we think this might be about if we look at the title? Kinetic theory, kinetic model of a gas. Well, it's about a gas, that's for sure. Temperature could be involved in it, yeah. So, don't write this down, just recall from memory. Pressure means how much something is pushing on something else. And the formula is what? For pressure? What is it? Say again? Yep. And the units? Newtons per meter squared, also called a Pascal. Okay, good. And the units are pascals. And remember we said 1 Pascal of pressure means 1 Newton of force pushing at right angles over 1 meter squared. That's a Pascal. Yeah? It's the same as that. Now, what shall we consider our ideal gas, or we shall consider our ideal gas to be as shown? Have you talked about ideal gases with Lorraine? Not really. Has she ever used that term before, ideal gas? No, you've never heard it in chemistry, but have you heard it before? Yeah, so ideal gas, there's a few things we assume about ideal gases. Yeah. Yeah, go ahead.
They don't react.
Oh, that's the chemistry thing, isn't it? Yeah. No, I don't care about that. Something else. Yeah, you're right. It doesn't react, I suppose. Yeah. What about else, though? You're saying something about temperature and pressure? Yeah, what about them?
They're like linear.
Yeah, they tend to have a linear relationship as they expand. So, the things we assume about ideal gas. Number one, we say it has a low density. It's usually a feature of an ideal gas. Number two, we imagine an ideal gas as just being colliding particles. That's normal. Number three, there's no attraction between them. So the particles aren't attracted. For example, it's not like a positive and a negative, or positive and positive. They're all neutral. No interaction, no attraction. Four, we don't consider gravity. So as we picture the particles moving around, we don't imagine that there's a gravity force pulling them down. Okay. So balls, small balls bouncing around in a box with no gravity. That's how I picture it. Okay, I picture a gas as like a box with little marbles just going dun, 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 around inside. Like a ping pong, yeah, just bouncing around. That's all it's doing. Now, in the exam, so here's a picture of it. In the exam, what they sometimes ask the students to do is to give 2 or 3 assumptions about the ideal gas. So I've given you 4 here, but usually the first 3 is what they like to see, that there's a low density of colliding particles with no attraction between them. Okay. But there's other things you can say too, like we ignore gravity, and also when they collide, the collision is perfectly elastic, meaning when they collide, they don't slow down. You know, but I mean, the first 3 points are enough for the exam. Low density of perfectly colliding particles with no attraction between them. Have you got those 4 assumptions? Yeah? Now, what I'm going to do next is a proof. The proof is kind of on the exam. Let me explain. The proof I'm going to do is very long. So they'll never ask you for the full proof in the exam. But they have asked students to explain parts of the proof. So they might say something, well, we'll see in a moment what they could ask for after I do the proof. So it is important that you know the proof. It is important that you understand the proof. It's not necessary that you can do the proof yourself perfectly, but it is necessary that you understand the proof well enough that you can explain it in the exam. Because they sometimes ask you to explain part of the proof. Okay? The proof is quite difficult. I'll probably make a mistake as I'm doing it. It has many, many steps to it. Okay? But we'll have a look at the proof now. The proof is about the ideal gas. Okay. Right, let's start the proof. So please stop me if there's a part you don't understand. So, we have our gas, which is in a box. And the particle is moving around, bouncing in the box like this. Okay? To make our life a little easier, what we'll do to begin with is we'll just look at one particle that is just going back and forth between the 2 sides. Boing, boing, just left and right like that, okay? So just to make our life a little bit easier with this proof, we start by imagining that it goes that way, then it bounces, and then it's back to the start like that. Okay? Right, so let's look at what happens with the... Okay, so let's just call this particle mass m, and it has a speed v to the right to begin with. What is the impulse, the change in momentum? Well, that will be mv minus mu. mv is actually minus v, because after it hits the wall, it heads left. And what's the u? It's v, positive v. Because it comes in at positive v and it leaves at minus v. Yes? So this is equal to minus 2mv. Now that's the impulse on the molecule, m. What is the impulse on the wall, w? Well, what does Newton's third law tell us? Do you remember? Reaction, yeah. In other words, if the molecule feels an impulse of minus 2mv to the left, then it meant that the wall felt an impulse of 2mv to the right. It's opposite sign. Okay? So you have delta P on the wall is 2mv. What I'll do next is I'll divide both sides by delta T. Like that. Now, what does delta P over delta T equal from Newton's second law? So let me just write here. This is Newton's third law. What does Newton's second law tell us here?
Force is...
It's a force, isn't it? That delta P over delta T is F. Is F, isn't it? 2mv over delta T. Okay, before I continue, I'll pause to let you write this much down. You got that? Yeah? Now, so what we'll use next, if I scroll down a little bit, is we have the formula pressure equals force over area. So that means force equals pressure times area. So you can say pressure times area equals 2 mv over the time. Now, if we think also about this triangle, distance, speed, time. I'm going to get rid of the time here. So distance, speed, time. What's time?
Distance over speed.
Distance over speed. So I'll just replace that t with, what do we say, distance over speed. The speed is v, and what's the distance? It's actually 2l, because one journey is 2 lengths. Okay, so that's kind of nice, because that means this 2 and this 2 cancels, and you get PA equals mv squared over L. Now A is the area of the wall. So what's the area of this wall that has one molecule hitting it? Oh, sorry, I should have really said this at the start. It's a box LLL. So what's the area?
L squared.
L squared. So you can change this into P L squared equals mv squared over L. So you can divide, and you get mv squared, multiply L cubed. I lost my, yeah, no I didn't. What's L cubed?
No.
Try again.
The
Volume.
volumes.
So you get PV equals mv squared, like that. Now, we need another switch. There's a small problem though, because in our picture, so I'll just put this here and then I'll just go to the side for the moment. In our picture, what's happening is the molecule is going like this, right? But it's not really doing that, is it? It's really doing something like this, bouncing around inside of it. So the difference between this is 1D and this is 3D. Okay? If you had the molecule heading in 3 dimensions, you have x, y, z. Let's call this speed here v, and here it is heading in 1 dimension, here it is here v. This is wrong. It's more like this, isn't it? The question is, how big is each of these sides? Well, let's call this x, this y, and this z. We can use Pythagoras. We can say v squared equals x squared plus y squared plus z squared. And you might say, well, how's that useful? How do I get x here? Because we don't know y and z. But what we can say is that x squared should roughly equal y squared, should roughly equal z squared. Why do you think I can say this? Why do you think I can say that the speeds in the x, y, and z are about the same?
Because there is nothing
Because
changing
there
the
are-
speed.
Yeah.
And there are other
Yeah.
particles just wrong. So always
Yeah.
moving around in the same area.
Yeah. So why does this mean that they're all the same? Well, think about the opposite, okay? Suppose that the z was bigger than the x and the y. Then it would mean the particles would tend to head upwards.
Mm.
Or if the x was bigger than the y and z, it means the particles would tend to head to the right.
There's nothing influencing them.
There's no differentiation between them, right? They should all be equally likely. So this means that you could get v squared is roughly equal to 3x squared. Yeah? So it means that x squared is roughly equal to v squared over 3. So in other words, if we want to switch from 1D to 3D, all we have to do is divide by 3. So if I go back to my picture here, this problem here is 1D. If I want to make it 3D, it's actually quite simple. All I do is change this into PV equals mv squared over 3. That's all. That's all I have to do. It's quite simple to switch from 1 to 3D. Okay. How far can I scroll down? Like to this bit, isn't it? Right. What does mv squared kind of look like? It looks like kinetic energy, doesn't it? Yeah. What I'll do is I'll change this to 2 over 3 times a half mv squared. So that's PV equals 2 over 3 kinetic energy. What's the potential energy here? Well, remember we said there's no gravity, so it's actually 0. So we can say it's 2 over 3 kinetic plus potential, so it's actually the total energy, because the only energy it has is kinetic. So this is 2 over 3 times the energy. So you arrive at, I think I got it, yeah, I just have to rearrange it. So E equals 3 over 2 PV. Now you might say, oh, but this is only for one particle. Well, it doesn't matter. If you had 2 particles, you just add the extra particles on. So you can just add the extra particles. So this kinetic energy just becomes kinetic energy 1 plus 2 plus 3 and so on. So it really doesn't matter about the extra particles. It doesn't affect the last step here. So after all that work, we finally arrive at this result. It says the energy of the gas is 3 over 2 times the pressure times the volume. Now, why is this result important? Well, is it easy or difficult to measure the energy of each particle and add them all up? Easy or difficult? Measure the individual energy of each particle and add them all up.
Impossible.
Impossible would be the best description. Measuring pressure and volume? Easy. So what you've done is you've changed the difficult concept, the total energy of all the particles in the system, into actually a simple concept. It is simply pressure times volume times 3 over 2. So this is like micro. It's, molecules. And what do we call this side here, the pressure and volume? It's macro, isn't it? Yeah.
Doesn't this formula assume that the particles are not colliding with each other then?
It does, doesn't it? But in total, it's not important that they collide, because all you're looking at is what happens with the wall. So since the collisions are perfectly elastic, no energy is lost. So you don't actually care about internal collisions. You only care about collisions with the wall. Okay. So I want you to finish writing this proof down, and then I'll give you a couple of questions that I've seen in the exam about this proof. We'll see if you can answer them. Is there anything else I need to say? Yeah, what makes it interesting is blah, 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 micro, macro. Okay.
I think we were a bit more.
No, I think we got that, didn't we? Because I remember writing Newton's second law down. So we're from here.
Do they ask questions about the changing of 1 dimension to 3 dimension?
You'll find out shortly. But yes. For what? For which part? You know the unit for energy, don't you?
Yeah, joule.
Yeah. You got that? So, here are a couple of questions which I've seen on the exam before about this proof. So one question is, explain what is the cause of the pressure on the wall. So what is the cause of the pressure on the wall?
Air particles and molecules.
The gas molecules colliding with the wall. But to be a bit more precise, it's the colliding with the wall and the changing of the momentum. You know, another question I've seen in the exam before was, what is the reason for the number 3 in the formula?
To balance out.
You don't have to be complicated like that. Yeah, why is the number 3 in the formula? That's another question I've seen in the exam. So what's the reason for the number 3? Because the gas is in 3 dimensions. In fact, if the gas was in 2 dimensions, then it'd be a 2. If it was in 1 dimension, it'd be a 1. If it was in 4 dimensions, it'd be a 4, and so on. So interestingly, this formula changes depending on the type of environment the gas is in. It's always in 3 dimensions. Well, no, sometimes it can be in 2 or 1. If you were able to get your gas confined into a thin container, where the container is only the height of the molecule, so it can't move up or down, then the formula would change. You know, can you picture like all the molecules lying on the table, unable to move vertically, just X and Y?
Is that technically possible?
Yeah, yeah.
Assume this one.
You can. Friction would be a problem with the wall, so usually these things are done at low temperatures. I think it's possible. It's possible to hold atoms into place. Yeah. What other questions have I seen in the exam? Yeah, so precisely what is the meaning of this formula? So let me just draw a picture to show you what it means. So imagine you had the gas, and the gas is spread out in a very big container. So the volume is practically infinite and the density is really low, it's practically 0. And then what you do is you take your gas and you put it into a smaller container of volume V. And the pressure is also quite low, at volume V and pressure P. In doing this, you have done some work on the gas of 3/2 PV. This gas has energy now. The energy was because you did work in compressing the gas down to this pressure and volume. Okay. So if you picture all the gas in this room, if I was then to take it and put it into this container, it'd have a volume and a pressure. How much work have I done in compressing the infinite size down to this finite size? This much work. That's a meaning of this formula. Okay. And if I was then to let the gas come back out, how much energy am I releasing in the process? This much energy. Yeah, it's okay. You get the idea? So it may seem like we know how much work is done to a gas when it changes pressure or volume from this formula. However, this tells us the stored energy in the gas and not the work done to distort the gas. So we have to be careful. If I took all the gas in this room and put it into this container, the energy would be 3/2 PV. However, if I took this container and started to do this, changing the volume, changing the pressure, it's not the same formula anymore. It's a different formula for when you start changing it like this. Okay? Do you understand the difference? So,
Yeah,
That's
for increase the pressure.
yeah, if I start increasing the pressure or decreasing the volume, the work in my hand is a different formula. It's not this one. Okay, that formula was only to put the gas in the container to begin with. Then it's a different formula for when I start changing things. Okay, let's look at that formula now. So, its proof is much easier. Okay, so to make our life easy, we imagine that we have a piston. Do you know a piston?
Mm-hmm.
you've seen it in cars before. So you've got the gas is in here, and the gas is at a pressure and a volume. And then what you do, you come along. Oh goodness, I'm drawing this horribly. Okay, you get the idea. And then, yes, you're right. You've compressed it. So the P2, and there's a V2 here, and these will be different. Okay. How much work have you done? Well, the formula for work is force times distance. So let's say that, oh, I don't know. We'll start off with length L1, and now we have length L2. We've made it smaller. Okay, so that would be F times, what's the distance? L2, L1 minus L2, isn't it? Yeah, L1 minus L2. L1 minus L2. Now, we can use the formula earlier for force. We said force is pressure. Pressure is force over area. I have to write this down, sorry. Pressure is force over area. So force is pressure times area. So this will be pressure times area. Yeah. Now there's a small problem though. There's two pressures. Which pressures do we use? You know? So I think for this proof, let me just double check. Yeah. For this proof, you assume the pressure is roughly constant. Now, it's not. Obviously, it's not. What is happening to the pressure when you squish it down? It's increasing, isn't it? But roughly, you can say it's constant, even though we all know deep down that the pressure has increased slightly. So we imagine that the pressure is roughly a constant number. The pressure from your hand. You know, you take your hand and you apply pressure. But we all know, as we apply the pressure, what happens? We actually are applying more pressure. It's increasing. We just imagine it's the same. Okay. I'm just going to multiply it in here. Who can tell me what A times L1 is and A times L2 is? Very good. It's the volume. So this is pressure times volume 1 minus volume 2. Or in other words, it's simply the pressure times the change in the volume. So we have our formula. The work done is equal to the pressure applied times the change in the volume you made. So you can see me here, I'm squeezing this. If you want to calculate the work done, it's the pressure in my hand multiplied by the change in the volume. That's how much work my hand has done. Yeah? Is that okay? You understand the formula? Now, we understand that this formula is not perfect. It's only estimate. It's pretty good though, because the pressure doesn't change too much anyways. Yeah? Okay.
So then when you get to the end.
Yeah, again to the end is a bit ridiculous because the pressure must be really big at the end. Yeah. So it's only really good for like what I'm doing right now, like small changes. Yeah. Now you don't need the proof in the exam for this one. You don't need the proof. So you can, if you like, you can just write the formula down if you want to. You see, this is the type of stuff that the biology students study when they do physics, these types of topics. What do you think this is important for in biology?
Blood pressure.
Blood pressure, yeah. So if you think about the heart, okay, it has a pressure and also what happens to the volume. It changes, and yeah. So you can work out how much work the heart is doing every time its volume decreases and increases. You can work out the work every time there's a beat.
And that could be also work beats per minute with the work.
No, well, no. But if you knew the beats per minute, you could get the work per minute, because you know how many times it contracts. You know.
1 point something.
I'm not sure.
Normal rate is around 90, I think.
Hence,
Well, I mean, at rest.
Yeah, what would it be for the heart for 1 minute?
average resting heart rate is like 60.
Yeah, so the work would be the pressure. I think the pressure is roughly something like, I don't know, 20,000 pascals, I think is the pressure of the heart. I don't know, it could be something like this. And let's estimate what would be the volume. Oh,
It's about the size of your hand.
it's about the size of your hand, isn't it? We said,
Your fist, yeah.
what's that about? 0.1 by 0.1 by 0.1, we'll say roughly. And then how many times would it beat per minute? We'll say 90. Okay, so yeah, I'm curious, what is the work per minute for the heart? How many joules of work is it done in a minute?
$1,800.
1,800 joules per minute. Yeah, and if we divide by 60 to get per second, actually, 30 joules per second, so that's 30 watts. So your heart is like a 30 watt pump. That seems a reasonable number, doesn't it? A 30 watt pump.
That's at rest. At rest.
That's at rest, yeah.
You start
Yeah. Yeah, yes, it increase. I think when our body is at rest, it's 100 watts. So if 30 watts is being used for the heart, then maybe I think it's like 20 watts is being used for heat and stuff, and then maybe 50 watts is for your brain. Brain takes up half the output, I think, you know. Okay. We don't actually need to do this formula because it's not on the exam, but what is on the exam is this definition. This is called 1 atmosphere of pressure. So you might not feel it, but in this room right now you have the air pressing down on your head. But you don't feel that because you're used to it. But it's actually a lot. The pressure, called 1 atmosphere of pressure, is 101.325 kilopascals.
And when you go 10 meters,
It reduces
it increases by 1.
if you go up or down.
Down.
Down 10 meters, yeah.
10 meters is 1 atmosphere, so at 20 it's
Are
12.
you sure?
Yeah.
10 meters is 1 atmosphere? I don't think that's right.
I studied for diving.
Oh, well, it's different if you're underwater. Yes, okay. So underwater, maybe each 10 meters represents an atmosphere, but not in the air.
No, I mean down.
Diving, yeah, okay, yeah. Now that makes more sense, yeah. Because that would mean, like, when we go down 3 floors, downstairs is 3
Yeah.
atmospheres,
Yeah.
so, yeah. It's not like this. Okay, so underwater, each 10 meters is an atmosphere.
Around, yeah.
Okay, that's a lot.
Maybe it's a bit more or a bit less.
Yeah. We are at sea level, you know, because Dublin Bay. So we would currently be at about this pressure in this room. Although because of the weather today, is the pressure higher or lower? Oh, you don't watch the weather?
Yeah, it's
Look at the weather. Is the pressure lower or higher today?
today's at
Oh no, don't look at your phone. Look at the window. Higher or lower pressure today?
Lower?
Lower pressure. Why?
because of the weather system. That's
Yeah, bad weather. Yeah, and then when it's sunny, higher pressure. Yeah, you watch the weather, don't you? Yeah, okay.
That's
Right.
why you have the barometers.
Yes, the barometers. Yes. Oh, there's a swimming question, but we don't need this for the exam. Yeah. So, the questions in the workbook, I think they're mostly explain questions. Let's have a look. Let's have a look. So let me see. The first one is not loaded for my phone. Now you might have a little bit of trouble with the first question because we haven't really talked about Celsius yet. But I wonder if anybody knows it before you start. It says here, knowing that the temperature represents the kinetic energy. So they're talking about this formula we did earlier. They said PV equals 3 over 2, oh sorry, no, I wrote that wrong. The kinetic energy is 3 over 2 PV. Oh, do you know what? No, we'll leave number 1. I'll move number 1. Skip number 1, just do 2 and 3 for now. I mean, you can try it if you want, but I recommend skipping it. So can you do number 2 and 3 for me now, and then we'll finish. Okay, I need to move 426. Let me add that to my to-do. Oh, no, I'll just do it now.